Ceiling-supported back harnesses are a commonly used safety device designed to reduce injuries in sheep shearing, but their effectiveness has not been properly quantified. The topic of this talk is our work to investigate their effect on features of motor control that are relevant to lower back injury. This work is supported by Australian Wool Innovation, who are interested in reducing injuries in sheep shearing. Lower back pain and injury is a significant global problem that's especially common in workers engaged in stooped work. One such occupation is sheep shearing, which is difficult labour where workers suffer severe rates of injury, with back injuries being the largest issue. The focus of this work is to evaluate the effectiveness of ceiling-supported back harnesses. You can see an example in the image on the right with the shearer in their typical stooped position and the harness suspended from above, providing some support to the torso during the task. These have been studied before, and it was found that the harnesses reduce joint torques and twisting movements in the lower back, but forces at the muscle level were not studied. Additionally, these numbers were extrapolated from very short durations for effects that are known to change over time. We wanted to address these issues by investigating motor control features from surface EMG and movement data extracted from the full working day. So our experiment involved instrumenting sheep shearers just while they performed their regular work. We observed 9 sheep shearers who completed a full day's work with wearable sensors attached, with one shearer observed over 3 consecutive days, and this data was also included as 2 extra subjects. We used an IMU-based portable motion capture system to collect kinematic data in the real working environment, and wireless surface EMG sensors were also placed on the erector spinae muscles at the level of the 1st and 3rd lumbar vertebrae, as well as on the multifidus muscle at the level of the 5th lumbar vertebrae. So from the pre-processed signals, motor control features that are relevant to lower back injury were extracted. These were the amplitude and mean frequency of the surface EMG, as well as the lumbar joint angles in flexion, twist, and bending. Motor control is task specific, which means that any dysfunction in motor control is also task specific. For this reason, these features were extracted from each repetition of the shearing task. So in sheep shearing, there are 2 main tasks, the catch and drag task and the shearing task, which are repeated across the day, seen here in the videos. So we extracted these features from each iteration of the shearing task using an activity recognition method that we previously developed. So the result is some event-driven sampling from each completed sheep from each of the 4 2-hour shearing runs, which is just depicted there in the image at the bottom. So we end up with 9 features that we label from A to I. The first 3 here are the EMG mean frequency features for the 3 muscles. Features D, E, and F are the EMG amplitude features. And we want to use these EMG features together to get an idea of muscle force and muscle fatigue, which are both associated with back injury. So here we use the joint amplitude and spectrum analysis, which has been shown to be quite accurate, even in real industrial environments, where if the amplitude increases along with the mean frequency, then this is indicative of increased muscle force. And increased amplitude accompanied by a decrease in mean frequency is indicative of muscle fatigue, and vice versa for the opposites. So the features G, H, and I are the kinematic features that we investigate, and higher values in each of these features are associated with higher rates of injuries. And to save some time, I'll say right now that the features from the L3 erector spinae muscle as well as the lumbar lateral bend angle have no significant differences between the harness and no harness case. So we won't look at these any further. But the full details are, of course, available in the paper. To properly analyze this observational study, we used a linear mixed model. So this is particularly helpful to deal with the unbalanced nature of the data, where each shearer shears a different number of sheep and may not complete every shearing run on each day. So what are they? These models are, first of all, linear, of course, which means we're just going to end up with the equation for a line, and they are mixed. The mixture is one of deterministic fixed effects and also random effects. Now, these random effects reflect the groupings and hierarchy in the data, as seen in this image, where we have each shearer, and then within each shearer, they shear a number of runs, and then in each of these runs, they're going to shear a number of sheep, and these can differ in the number of runs as well as the number of sheep. So these this hierarchy allows us to have a comparison both within within groups and across different groups. So in this case, the shearers that use back harnesses and the shearers that don't use back harnesses, as this is their personal choice. So we put these together to get a regression model for each feature, and this is our line, where R is the time of day variable, which is the shearing run number from 1 to 4, and H is dependent on whether the shearer uses a back harness or not. Then beta, alpha, delta, and gamma are the fixed effects. Beta is just the intercept of our line, and alpha is the change in that intercept for shearers that use harnesses. Delta is like the baseline slope of our line, and gamma is the amount that the slope changes for shearers that use back harnesses. Then at the end, A, B, and E are the random effects. These are Gaussian random variables with a zero mean, where A is the distribution of the feature across different shearers, B is the distribution of the feature across runs, and E is the distribution of the feature across each sheep in the run, which is the residual in our case. So we fit the model to the data, and then we get a significance result for each of the fixed effects. So here's an example of the results from one feature with a significance test for each fixed effect. And here we're mainly interested in the alpha and gamma parameters, as these indicate the differences between the harness and no harness case. So you can see these tables for each feature in the full paper, but for this talk, I'm just going to show you graphically in the next slide. So first of all, looking at the L1 erector spinae features now, the mean frequency increases with the use of harness, which is also accompanied by an increase in EMG amplitude. So through the JASA analysis method, this indicates that the active muscle forces in the L1 erector spinae muscle are actually higher when using a back harness, and both the amplitude and frequency of this muscle decrease over the course of the day when using a harness, which indicates that over time it's likely that load is shifting away from this muscle as well. And this is quite similar for the multifidus muscle. However, the increase in EMG amplitude is not significant here, the p-value for the alpha fixed effect. For the kinematic features now, there was no significant difference in the lumbar flexion angle, but we note here there are large inter-individual differences noticed in this feature. And for the lumbar twist angle, there is a significant decrease in lumbar twist with the use of a back harness. So there was an increase in muscle force that we noticed in lower back muscles with the use of the harness, and this was accompanied by a gradual load shift away from the muscle over the course of the day. Now, this effect is likely to be a response to manage the muscle fatigue from the higher forces. And this could potentially worsen some avenues of injury risk when the harness is used. So the kinematic features were improved with the harness, which with a significant reduction in spinal twisting, which is associated with injury. Now, previous studies indicated that the back harness reduced joint torques. So in order for that to be consistent with higher active muscle forces, then that means that the back harnesses is likely causing a shift of load away from the passive tissues in the back towards the active muscle forces. Now, this is plausible as the flexion relaxation phenomenon has been noted in shearing previously, and the harness may prevent shearers from entering the range of motion where relaxation occurs. And this would be actually consistent with a decrease in spinal flexion. And there was perhaps some slight evidence of this, but with the really large inter-individual differences, then that result was not significant. Yes, and it's possible then that increasing the support provided by the harness could actually further reduce the joint forces, with the potential of then also reducing muscle activity instead of increasing it. And this could further improve the kinematic benefits while reducing the drawback of the increased muscle activity. And that's something that we would like to look at in our future work. So thank you for listening to this talk. If you'd like to know any more details, please read the paper, and my contact details are available here again at the bottom of the slide.